Okay, this is part 2 of this video. We're going to be talking now about how to measure the capacity of the lungs to ventilate. We've talked about already the impact of elevation on VO2 max. We've talked about the physiological roles of the pulmonary system in ventilation and acid-base balance. We've talked a little bit about how ventilation occurs. Now we're going to focus on how to measure it. When measuring ventilation, we look at a couple of different capacities, and we do so with something called spirometry. Now, as illustrated in this picture over here, we got a guy that's breathing into a tube, and this tube leads into a computer that measures how quickly the air is moving out of his mouth. And we can measure it over here. So on this diagram on the right, we have lung volume as the y-axis, and then the x-axis is time. If you look at the lung volume, at rest, he's doing a normal breathing. So his lung volume at rest is usually somewhere around 200 or 2,500 milliliters. And so as he breathes, he inhales, the volume increases, he exhales, the volume decreases. So he's doing just normal resting breathing. And then here he does a maximal exhalation. So the volume of the lung is decreasing. Look, when he does a maximal exhalation, he can't get rid of all of the lung volume. There's still some volume that's left, and that's partially because you can't really collapse your lungs, right? You need to have some volume there, and you can't collapse like the trachea and the bronchi and all that. And so you don't ever maximally exhale. If you did, you'd probably be in danger. And so he did this maximal exhalation, doesn't get all the air out, that's normal. And then he starts to breathe again. And now he does a maximal inhalation, and he maxes out his lung volume somewhere around 6,000 milliliters. And then he exhales and goes back to normal breathing. Now he does a common test that we call a forced vital capacity test. This is one that you do on patients with COPD or lung disease, asthma. And you do a major maximal inhalation immediately followed by a maximal exhalation. And then you go back to normal breathing. So the normal breathing, or the depth of your breath, whether it's normal exercise, whatever it is, that's called tidal volume. And that's the difference between this peak and the trough at rest, or the peak and the trough here. When you exercise, your breathing, the depth of your breathing will increase, and it'll just move up and down greater, and you'll have a greater tidal volume. Of all the things that you need to understand for XPhys, tidal volume at this point is probably the most important. And the simplest explanation of it is that it's the depth of your breath. Another important thing is the vital capacity. And vital capacity is the total amount of lungs, the maximum amount that you can inhale and exhale. And so that'd be the difference between this peak here, the maximal inhalation, and the trough, the maximal exhalation. And so you can see here that on this person it's somewhere around 5 liters, which is pretty good. There are several other capacities and volumes that you should study in your textbook, but that's all I'm going to highlight for the purposes of our lesson today. If you go on in a career in medicine, physical therapy, respiratory therapy especially, you'll need to understand these volumes very well. But tidal volume will get us where we want today. Now, here's an explanation of all those different volumes and and capacities. So you can study this. This comes right out of your textbook, so you can look at that as well. A normal resting tidal volume is somewhere around 500 milliliters. As you exercise, that will increase up to 2,500, maybe 3 liters is about the biggest I've seen during exercise. Suffice it to say that tidal volume will increase when you're exercising. So how do we measure how much air is coming in and out of the nose, or mouth and nose, when we exercise? And that's called pulmonary ventilation, or minute ventilation. And it can be indicated as a V with a dot over it. The V means volume, and then the dot is a rate, so the volume per minute. Or most of the time I'll refer to it as V sub E. So V, capital E on the bottom here. You can call it pulmonary ventilation. Sometimes you'll hear it called minute ventilation. It has a lot of different names. Really what it means is how much air is coming in and out of the mouth every minute. And the way we measure that is by measuring the depth of your breath, or the tidal volume, so V sub T, tidal volume, and multiply that by how many breaths you take per minute, right? So we have, if you're breathing in I can illustrate it here. If you're breathing in a tidal volume of 0.5 liters and you're taking 15 breaths per minute, that means you have about 7.5 liters of air coming in and out of the lungs per minute. Now when you exercise, that depth of breath will increase, so tidal volume in this case went to 3.5 liters per minute. Breathing frequency also increases up to about 45, so the minute ventilation is 158 liters per minute. Now that's impressive. That's 158 liters of oxygen, liters of air, I should say, in and out of the blood, in and out of the lungs every minute. Think about that in terms of Coke bottles. That's a lot. And this is a realistic number. These numbers here are data that I collected off of someone during a VO2 max test. You can get a lot of air in and out of those lungs every minute. But getting air in and out of the lungs isn't necessarily what we care about the most. We actually care about how much of that air actually makes it to the alveoli. And so what's more important for exercise performance and for physical function is alveolar ventilation. How much air you're getting down to the alveoli every minute. And it's highly related to minute ventilation or pulmonary ventilation, but there's an important difference here. So the equation is very similar to the equation for minute ventilation, pulmonary ventilation. We have tidal volume and frequency, but we're taking the tidal volume and we subtract something called V sub D, or dead space. What dead space is, it's the volume in your lungs that doesn't exchange gas. Right? When we get down into the trachea and the bronchi and all this conducting zone, we don't get any gas exchange there. So it doesn't matter so much for getting oxygen in and out of the lungs. So when we're calculating how much actually makes it to the alveoli, we subtract out the dead space. So we subtract out the volume of the trachea and of the bronchioles and bronchi, and then we multiply by the frequency. In a normal healthy adult, for the purposes of our class, we're going to assume that the dead space is somewhere around 150 milliliters. Now there are different things that can happen that can increase the dead space in disease and other conditions. The higher your dead space, the less effective your breathing is, right? But for the purposes of this lecture, we're just going to assume in healthy lungs is about 150 milliliters. Okay, so to calculate it, to calculate alveolar ventilation, if we had a tidal volume of 500 milliliters, then we would take 500 minus 150 and multiply that by the breathing frequency. Your alveolar ventilation is always going to be less than your pulmonary ventilation because you have to subtract dead space out. And this graph is just showing what happens to the different volumes as you exercise. Increasing minute ventilation or pulmonary ventilation as you exercise, you have an increase in tidal volume. That's really all that's for. I guess it's kind of a wasted slide here. So what happens to our ratio of alveolar ventilation to minute ventilation, pulmonary ventilation when we exercise? As I mentioned, alveolar ventilation is always less than pulmonary ventilation. But when we exercise, the ratio of those two changes. And what the ratio tells us, like the ratio of alveolar ventilation to pulmonary ventilation, tells us how much of the air we're breathing actually makes it down to the lungs. So at rest, if we have an alveolar ventilation, a ratio of like 70% is kind of right in the ballpark, right? If we have a dead space of 150 milliliters and then an alveolar or minute ventilation tidal volume of about 500 mils, we come out to a ratio somewhere around 70% of our ventilation is actually making it down to the alveoli. Now, when we exercise, the depth of our breath, our tidal volume, increases, right? So our tidal volume increases with exercise, but the dead space stays the same, or it could even go down a little bit. So that means that when we exercise, we actually get more gas exchange per breath. We're getting about 90% of the air we breathe in for our deep breathing that actually makes it down to the lung, to the alveoli for gas exchange. So let's talk about why this matters. Alveolar ventilation versus minute ventilation. I have two breathing patterns here. Both of them have a minute ventilation of 6 liters per minute. Okay. Pulmonary ventilation, 6 liters of air coming in and out of the lungs every minute. In pattern A, we have someone with a tidal volume of 600 mils per minute, and they're taking 10 breaths per minute. Dead space, 150 mils, just like in the bottom here. But in pattern B, now we have someone that's taking shallow breaths, about 200 mils per minute, but they're breathing much more frequently at 30 breaths per minute. So they have the same pulmonary ventilation, but they're getting there in different ways, right? Same amount of air coming in and out of the lungs, but pattern B is doing it with rapid, shallow breathing. Now so the pulmonary ventilation is the same, but let's look at how much actually makes it down to the alveoli. And that's quite different. With our pattern A, we're getting about 4.5 liters of air down to the alveoli a minute. So alveolar ventilation, 4.5 liters per minute. But with the rapid, shallow breathing, because we're subtracting the dead space, look at this, we take our 200 milliliter tidal volume and we have to subtract out our 150 milliliters of dead space. That means only 50 milliliters per breath. It's actually making it down to the alveoli. That means, in the end, that only 1.5 liters of air per minute is getting down to the alveoli. It's not very effective. So if you want effective breathing, deeper breaths, less frequently, right? Now, another thing when we're talking about dead space is you can artificially increase your dead space. If you have, let's say, a giant snorkel, to get that air down to your alveoli in this giant snorkel, you have to breathe in this whole volume of the snorkel, and that's increasing your dead space astronomically, right? And so that would mean that you have to take a huge deep breath to get any of that air down to the alveoli for gas exchange. That's why you don't see people scuba diving with 30-foot long snorkels or 50-foot long snorkels, because that's a huge amount of dead space that they have to overcome to actually get air, fresh air, to their alveoli. Dead space is very important when we're talking about breathing, and especially if you're talking about breathing on devices like a scuba tank or anything like that. That's all we're going to cover for today. Remember, we've talked about the influence of the oxygen cascade on VO2 max, especially at elevation. Talked about the physiological functions of the pulmonary system in gas exchange and in acid-base balance. And we've talked about how you ventilate air in and out of the lungs. Okay, that's it. I hope you have a great day.